part F. This is our second round. Yeah, I mean, on this PDE topic. Yeah, in module 1, we use one part, part C, to get a basic knowledge of PDEs. So this part, we need to solve PDEs by Laplace transforms, because we have learned Laplace transform. Yeah. So after the midterm, we have another round. PDE, we solve by Fourier transforms. Yeah. All right. F.1, first, but we need to do preparation, Laplace transform. We need to learn some important formulas before we can solve PDEs by Laplace transform. So first, Laplace transform on Heaviside function. So this function very special, but very useful in engineering problems. Yeah. So let's study this special simple function first. Definition of Heaviside function. Yeah, very simple. Definition. Yeah. See, it's a piecewise constant. Yeah, we can call it piecewise constant. Yeah. All right. Yeah. Two pieces. Yeah. When t less than a, it's 0. When t greater than a, it's 1. Yeah. All right. All right. So that's the u function, u of t minus a. Yeah. And yeah. So here that a parameter we use to adjust the starting point of the second piece, this piece. Yeah. Yeah. Because sometimes we need to control. Okay. Use this parameter to control which part of the function we want to take. Yeah. Cut off. Yeah. So, all right. The simplest Heaviside function, like this, a equals 0. Okay. Yeah. So that's u of t. Yeah. U. Yeah. U. Yeah. Because we call it a unit step function. A unit. Okay. Yeah. Step. It's a step. Yeah. Like a step. Unit step function. U of t. Like that. Yeah. Yeah. So this function. Yeah. Because in engineering problem, many of our functions, the right-hand side, R of x, that functions, we commonly used piecewise functions, multiple pieces joined together. So that's very common in the engineering problems. In that situation, we need to use this u function to help us join multiple functions. Yeah. So later you will see. Yeah. So very easy. Use this u function. Yeah. Then for the with arbitrary a, we can use. Yeah. Here you need to first you need to see u of t minus a. The starting point of second piece is at a point. Yeah. Can you see it? Yeah. It's very easy to see it because when t equals a minus a is 0, then 0 point, that's based on this unit step function, that's the starting point of the second piece. Yeah. Here you can, you shift, so here is the shape of this step function shift by a units to the right. Yeah. When you use t minus a, t plus a to the left. Yeah. The opposite direction. Yeah. All right. Yeah. So why we need to stay here? Yeah. 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 For solving ODEs. Later PDEs. Yeah. So ODEs first, then PDEs with complicated right sides. R function, R of X function at the right hand side. Of considerable engineering interest, such as, so there are these things. One is a single wave, that function. We know wave, many periods, right? Periodic functions, many periods repeated. But in engineering problem, single waves used a lot. Only one period of wave. Only one period of wave. So that's the single waves, one type. Another discontinuous driving forces. Driving force, so that the spring system, mass spring system, the driving force right hand side, the driving force is discontinuous. But how do you join multiple parts discontinuous function, right? So that kind of thing, discontinuous. Each piece is continuous, all right? Then another piece continuous. Then continuous. So multiple pieces. So we call it piecewise continuous. The whole function is not continuous. So there are many discontinuities. So those functions we can use Heaviside function to represent easily. All right. Then periodic inputs. So for the periodic inputs, because sometimes only part of the periodic inputs. So not the complete periodic inputs, part of it. So how to get a part of it? So we use this function. Multiply a periodic function. So we can get a part of the periodic functions. All right. Now, first, we want to calculate Laplace transform of Heaviside function. Very easy. This definition, then we apply the definition of Laplace transform. Calculate the integral on this simple function. So by the formula, Laplace transform of u of t minus a, this general case. All right. In the formula, but here, this I took the screenshot from the textbook, but I noticed there is some error here. Because when you look at this part, u of t minus a, because when t less than a, all zero, so you can throw away. The starting point is at a, okay? The non-zero part, starting point, starting from a, so this lower integral limit should be a, not 0. Okay? Because starting from this a, then your Heaviside function becomes value 1. Before this point, value 0. So it's gone. So we correct it. Then, integration by parts, we don't need integral. We just calculate the integral, right, directly. Because here too simple. We just calculate the infinite integral directly because the limit exists. The limit at infinity exists. We know S positive. Now, in our Laplace transform, our S is positive. So e to the negative st, its limit is 0. So then, you can see, the formula is this: e to the negative as over s. Laplace transform, very simple. All right. Next, we need to consider the Laplace transform on the functions containing this u function. The function, containing u function. Because usually this u function is used together with some f function, little f function, used together. Because the main part is the f function. The main content is the little f function. But we need to use u function to chop part of the f function. So that's why we use this u function. All right. So here, now we need to study f. Let little f 0 for all negative t, and consider this structure. We'll also shift f by a units to the right. Okay. All right. Shift it. So let's use a graph to understand. The first graph A is the graph of the original little f function, 5 times sine of t. 5. Okay. Peak. So one period here, shaped like this. Sine t, 5 times. All right. Then, we try to see what's the difference. B and C different. B, we do not do shift on this little f function. We only do shift on u function. But a C, we do 2 units shift to the right, both f function and a u function, to let you see the difference. All right. Because first, we copy the graph of f function from the A case. Then we use u function to chop it, to take part of the graph. So starting point at this 2. Start at 2 and chop it down. The left-hand side throw away. Right-hand side is 0. Okay? Left-hand side is 0. So starting from 2, unit 2, then 1. Keeps the remaining part of the f function. So that's part of B. Part of C, at the same time, we need to also shift f function by the same number of units to the right, 2 units to the right. So you can see when you do that shift, the whole period is preserved. One period, the whole period is preserved. So after we chop it at point 2, so we keep the whole period. So the difference. All right. Then, second shifting theorem. We learned the first shifting theorem, right? So in our, we learned the first shifting theorem. But this place, second shifting theorem. All right. Second one, we need to include this u function. The first one, no u function. All right. So f tilde, so f transform, little f, capital F transform. All right. But this, now we consider f tilde, f tilde, so we multiply the u function to the f, with parameter a. All right. Has the transform, Laplace transform, okay? Has the Laplace transform. An extra factor, e to the negative as. This comes from the u function. And times capital F of s from the original little f function. Yeah. All right, so that is Laplace transform of the product of these two functions. Here you can see the impact of u function. You get this extra e factor. Yeah. And then you take inverse Laplace transform on the right-hand side, so that you get that. So you have, this pair of Laplace transform and the inverse Laplace transform related to the u function. Yeah. Yeah. We can prove it easily. Yeah. We just, plug in the formula. We can prove it easily. Yeah. Oh, here, let's review the first shifting theorem. Yeah. First shifting theorem, Laplace transform on, so here you can see, e factor times at multiply this original little f function, shift at the s side, capital F s side, you have shifting. At the t side, you have an e factor. You see? Yeah. Some, interesting relationship. Yeah. Which side? Yeah. All right. Yeah. So these two shifting theorems. All right. Yeah. Let's prove quickly. Yeah. I mean the two versions. Yeah. All right. The definition, by definition, so that's the capital F function. Yeah. Then multiply inside, so here you can see in this integral, this tau is the dummy variable, right? Tau is the dummy variable. So as we treat as constant. So e to the negative as, this is a constant number, so we can, multiply it inside the integral function. Yeah, so then we combine, simplify. Yeah, so we get it like this. Yeah. All right. Then, do the variable substitution, right? Yeah, because this tau plus a. So you use t. Yeah. So you do variable substitution. This tau plus a, you replace it by, because it is just a dummy variable. So you make this part t, do variable substitution. So tau equals t minus a, original tau. And when you do that variable substitution, 0 is shift to a, right? So here your integral lower limit should be a. Yeah. All right. So then after this one, all right, Heaviside function, right? Yeah. So when you look at this form, starting point at a. Here you can see that's just the Heaviside function. U times shift by a times f shift by a. See? Yeah. So this one you can quickly connect to this left-hand side. Yeah. The definition of this left-hand side. All right. Yeah. So you prove it. Yeah. So you write it. So this is f tilde. Yeah. So in this way, you can put the lower integral 0. Yeah. All right. Yeah. So that's the proof. Okay. So this calculation, simple proof of this formula. Yeah. Then straightforward way you can get a second one. Yeah. All right. So that's it is very simple. Yeah, but it is a very useful tool we can use to calculate Laplace transform and the inverse Laplace transform. Yeah. All right, so these two shifting theorems. Yeah. All right, so next, let's do some examples. Yeah. Let us apply all the formulas we have learned at this point about the Laplace transforms to, calculate a few more examples. Then, after that, we will solve a few PDE problems. All right, F.2, examples with Heaviside function. Yeah. All right. Yeah. Given Laplace transform of a function. Yeah. All right. So find the inverse transform f of t of, so our capital F function given. Yeah. Yeah, see? Yeah. It looks a little complicated, right? Yeah. So let us spend some time to understand the structure of this capital F function. Yeah. After we understand the structure well, so then we can determine what formulas we should use. Then we can do the calculation. Yeah. 3 fractions, the structure, 3 fractions. So let's look at it one by one, because by the linearity principle, we can calculate the inverse Laplace transform of each fraction one by one. Linearity principle. Yeah, that's first thing. Second, the numerators is some e function, right? E to the negative some expression. Yeah. And that corresponds to our second shifting theorem, right? Yeah. Second shifting theorem, the e function term appears at the s side. Yeah. Yeah, s side. So this part we can apply our our second shifting theorem. Okay? Yeah. So we can do this way. Yeah. Before we apply the shifting theorem, second shifting theorem, let's calculate inverse Laplace transform with numerator 1. Okay? Numerator 1 over s squared plus pi squared, we calculate inverse Laplace transform to get little f, right? Little f. Then we add that e part back so we can apply second shifting theorem. Yeah. So each one we do that way. Each one, the first time we calculate inverse Laplace transform with numerator 1. Numerator 1. Numerator 1. We know how to calculate, right? Yeah. So then apply second shifting theorem. All right. Numerator 1 here corresponds to sine function, right? Yeah. So if you have some impression, from our formulas, basic formulas we learned before. So sine function, this power function, right? Yeah. So this structure corresponds to a power function. But the power function s plus 2, another shift part, s plus 2. That's the first shifting theorem. How to handle the s plus 2 part? First shifting theorem will tell us how to do that. Yeah. So based on this understanding, we can take care of all the parts. Yeah. All right. So let's do it. Solution. Yeah. So this for sine formula we need to use. So the first fraction, second fraction, we need to use the sine formula. T, so the second one, yeah, T 1 over S squared, the third fraction, yeah, we need to use this T, this formula. Yeah, two basic formulas. All right, then this is the second shifting theorem. We need to use, you know, the three numerators, E functions, yeah, E functions, right? Yeah, E function. We need to use the second shifting theorem. Yeah, all right. Yeah. Then first shifting theorem. So here, this is the first shifting theorem. We need to use here S plus 2. This A is A negative 2. S minus negative 2. So S plus 2. So then apply the first shifting theorem. We have this e to the negative 2t times little f function. See? Yeah. So these four formulas are the main formulas we need to use to calculate this inverse Laplace transform of capital F function. Yeah. 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 Try to, you know, practice, you know, yourselves. Yeah. All right. So now let's do the work. Yeah. First part, yeah, do preparation, yeah, because based on this formula, basic formula number 8, the numerator we need to have a pi. Okay? Yeah. But to get a numerator 1, we divide it by pi both sides. All right. So we get this part already. Yeah. For the first two fractions, we can apply this formula. All right. Then, for the first fraction, inverse Laplace transform negative s, we apply second shifting theorem here. Yeah. Negative a equals 1, right? Negative as, a equal to 1, so t minus 1. U here also t minus 1. Yeah. So that's the first one. Similarly, the second one, just change 1 to 2. Okay? Change 1 to 2. Yeah, second one, change 1 to 2. Yeah. Yeah. So then the last one. Okay, let's do the last one. Last one, yeah, because there is a first shifting theorem. So we also need to take care of the shifting part for the first shifting theorem. So we calculate inverse Laplace transform of 1 over s squared. 1 over s squared. Okay? The basic formula number 2. So we get a t. Yeah. After that, we apply first shifting theorem to get, you know, f of s minus a, yeah, s minus a, s plus 2. Yeah. Yeah. So we need to multiply the e function at the t side. Yeah. E to the negative 2t times t. Yeah. All right. But that is the numerator 1. Then numerator e to the negative 3s. You need to apply second shifting theorem another time. Yeah, similar to the, you know, these first two fractions. Yeah, we just apply another. Yeah. Then, all right. This time we do, yeah, so this side, yeah. F function, U function, right? So F function, this is the F function, okay? This is the F function. So for F function, we replace t by t minus 3, yeah? T minus 3. Yeah. Replace t by t minus a. Yeah, because a, so here, a is positive 3, right? So e to the negative s. So a is positive 3. So t minus a, t minus positive 3. Yeah. Replace t by t minus 3. Yeah. Yeah. Then times the u part. Yeah. So when you do these solve these problems, so you need to be very careful. A lot of details, shift here, there, replace, things like that. Yeah. All right. So the last step, we combine the results of the inverse Laplace transform of all the three functions, adding together to get a final result. Yeah. All right. So that's the last step. Yeah. Answer. Yeah. All right. Yeah. So the formula pretty long, right? Like that. Okay. Yeah. Yeah. So when you solve this kind of problems, after you get this last result, it's good enough. But here we like to draw the graph of this function. It looks very complicated. So we want to draw the graph of this function and see the graph is like this. Then 0. Another. See? So why is that? So let me explain. So why the graph is so strange? This part is 0. Okay? This is the strange part. But these two pieces looks all right. But how about this part? Actually this part, you can see. Now let's focus on this piece. All right. Interval. So here we want to understand this Heaviside function u. All right. So you can see in the u functions we use it in three different places. But the first one shift to 1. The starting point is at 1. Second, starting point at 2. Third, 3. So you can see, so 1, 2, 3. So you have the pieces before 1, 0, all 0. Okay. Before 1, all three terms are 0. Okay. So that's what easy part. Then before 2. Before 2, the first term non-zero, the second term before 2, right? The second term 0, right? Third term also 0. Because the second term, the function starts non-zero at the point 2, at this point 2. But before point 2, 0 value. So here, between interval 1 and 2, you only draw the graph of the first term. So that's sine. Okay. So determined by the sine part. Then, now let's look at between 2 and 3. Between 2 and interval 2 and 3, first term non-zero, second term non-zero, third term 0. Third term 0. So you do not need to look at draw the third function, the graph of the third function. You only draw the graph of the first two functions. Okay? All right. The first two functions, you can see, their difference is 1 unit shift, right? The first function, you shift 1 unit to the right. Second function, you shift 2 units to the right. So the difference is 1 unit to the right. The second term, you shift 1 more units. Okay. All right. But that 1 unit difference occurs at the t part, but you need to multiply extra pi, right? That means 1 times pi, actually, that's the half period, right? Sine function 2 pi periodic, 1 period. The length of 1 period is 2 pi. But here, you only shift the part is pi, half of the period, okay? Yeah, half of the period. This bump, this is half of the period, right? The other half lower side, right? The other half lower side. You know, this is the 1/2 of the period. Then the other half, yeah, lower side. So for the graph between 2 and 3, if we draw the part from the first term, we need to draw it the lower side, right? Yeah, well, you know, yeah, like that. Yeah. Then, if we draw the graph of the second term, we need to draw the upper half, right? Yeah, yeah, because we shifted half period to the right. So the, you know, the positive bump, yeah. Then, adding together the positive part, negative, the shape exactly the same, right? Sine function shape. The basic shape is the sine function. And the same period, right? Same period, sine function. Yeah? So the positive half, negative half cancel out. When you add them together, that's why between 2 and 3, you see 0. After cancellation, you have 0. All right? Yeah. Then, now, after t greater than 3, so for this part, the graph of this part, can you see? So to draw the graph of this one, the sum of the 3 terms, can you see? So this tail part, yeah. So this tail part all comes from the third term. Can you see that? Yeah. Can you see that? Because after 3, the first 2 terms, yeah, you need to add the values from first 2 terms, but they also cancel out. Okay? Yeah. So the first 2 terms, so after this point 2, they cancel out everywhere. Okay? Positive, negative, exactly the same value, so they cancel out everywhere. So the sum of the first 2 terms always 0 after 2. Okay? Yeah. So that's why after 3, the graph of this part only comes from the third term. Yeah, so that's the, yeah, you know, how we understand this graph. Okay, all right? Yeah. Yeah, so that's our first example. Yeah. Yeah, second one, we solve a RC circuit problem to a single rectangle wave. Yeah. So our, you know, right-hand side function, yeah, right-hand side function corresponds to the, you know, that battery or generator, right? Yeah. So that that part, yeah. So that function is a single rectangle wave. Yeah. So another commonly used function in engineering problems. Yeah. All right. So the components, you have C component, R component, then V. Yeah. V function. This V function is given in the single rectangle wave. So this is called a single rectangle wave. Yeah. Wave. Yeah. Only, one single wave. Yeah. Not repeated. Yeah. Yeah. So very simple. So let's do the calculation. Yeah. Find the current little I function, I of t, in the RC circuit figure. Yeah. So the voltage V0, single with voltage V0 is applied. Yeah. Yeah. So this value is capital V0. Yeah. All right. First, let's write the ODE. Yeah. Using this shape, we need to use Heaviside function. Yeah. 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 All right. Yeah. And let's represent this part first. This part, can you see V0 times in this brackets? You take the difference of Heaviside function with two different shifts, A shift and a B shift. Yeah. So that's why in the previous slide I explained the graph, all the details. Yeah. Because that part can help us understand matching the function and the graph. Here we need to match the function. Yeah. So the function given in this graph, but now we need to get the expression. Yeah. Expression. How can you see this expression corresponds to this graph, right? Yeah, we need to understand this part carefully. All right. Yeah. V0 part easy, right? So, original function is 1. Yeah. You multiply V0, capital V0. Yeah. Let's just look at the bracket inside the part inside the brackets. All right. Yeah, two terms, right? Yeah. So using the similar way we did analysis in the previous slide. Two terms adding together. Okay. Yeah. The first term starting non-zero from point A, right? Yeah. Before A, both terms 0. Yeah. Starting from A, the first term 0, but first term non-zero, second term 0, right? Yeah. Starting from A, between A and B, only the first term has contribution. Between A and B, second term has no contribution. Because the part before B, the second term is 0. Yeah. So if we look at the interval between A and B, we only look at the value from the first term. Yeah. So that's why you draw 1 times capital V0. That's the, what do you see here? All right. Then, after B, both terms non-zero, right? Yeah. So first term non-zero, second term non-zero, but they have the same values, right? First term equals 1, second term equals 1. They have the same value, but you take the difference. 1 minus 1. So after B, 1 minus 1 cancel out. You get a 0. That's why after B, you have all 0. All 0 values. Yeah. So that's the way how you see it. Okay? How you see the shape. Yeah. So that's another reason you can see if we use the Heaviside function, we can represent this. Yeah. So here we call the single rectangle wave, right? Yeah. So we can represent single rectangle wave easily. Yeah. But there is another name people also used frequently. Yeah. People call this function shaped like this: 0, 1, 1. The 1 only on the interval between A and B, called a window function. Yeah, there is a window, right? Yeah. Yeah. So you cut off this part of a given function. You only take this window area. Okay? Some people also call it a window function. All right. Let's look at the equation. Equation R component. So we call the voltage drop, right? Remember, here we need to recall the Kirchhoff theorem, right? Kirchhoff theorem. The voltage drop, okay? Going through, so the current, going through all the components. So you need to add up all the voltage drops, then equals this V. V function. So the voltage drop of the R component, this formula. Then C component, capacitor, C component, Q of T over S. Q, the quantity, right? The quantity of the electric charge, amount of, amount of electric charge stored in this C device, capacitor device. That amount, total amount, this little q function. The q function calculated, we use integral. Total charge, we have integral formula. Integral on this little I function. Integral, we'll get a q function. All right. So this is our ODE. All right. Then, so there we need to, because q function, I function, q function, two different symbols. Now we want to use the same symbol, right? But we have a formula for that q function. So the total charge can be calculated by the integral from 0 to t, that I function, current I function. Okay? So after the replacement, you can see only little I function is unknown, right? Only little I function is unknown. All other numbers all known. So we only need to solve this equation. But this equation, here you can see no derivative, but you have an integral. So we call it integral equation. So not a differential equation, an integral equation. But we know integral is closely related to the derivatives, right? So one way you see it, if you take the derivative of this integral function, you get an I function, right? You take derivative. Take derivative. Here, for the Zoom side students, to let Zoom side students see. When you take the derivative of this integral function, you get this I function. Okay? So that result, basic result, in calculus we call the fundamental theorem of calculus. Fundamental theorem of calculus. Very fundamental. Okay? Very important. But very basic. So in that way you can see, if you treat this whole integral as one function, the q function, right? Little q function. Then you have the q prime, right? You replace I by q prime. So you get an ODE, right? So you get a simple ODE. All right. But here, that is one way. So you keep the q function. You replace the I function by q prime function. You can also solve it, right? So there is another way you can write this ODE as R times q prime, q prime, if I put a t there, plus q T over C equals V of T. Yeah, so you have ODE of a different form, right? Yeah. Yeah, but here, currently, we use the I form, okay, not Q form. So there are two forms you can write. So you have two different ways to solve this problem. Yeah, both work. Yeah. All right. So when you use this I form, integral, we learned the Laplace transform of integral, right? We have that formula. We learned Laplace transform of integral formula. We learned, right? Yeah. So we can do it, yeah, because we want to apply a Laplace transform to solve these equations. Yeah. So we don't worry about the integral. Yeah. All right. All right. Yeah. So let me see. Yeah. Yeah. All right. The formula preparation. Yeah. Yeah. So it's at the break time. So let's take a break. After the break, let's complete the solution.